Welcome to the third movie in the KiMoPack tutorial. In this movie we're going to use the main tool, raw plotting and simple fit, to analyze how our data and to do a simple and fast fitting. This is usually the tool where I start to look on data with, because it kind of combines looking and also fitting. As always, we start by copying a workflow tool into our project folder and opening this workflow tool. I always rename the workflow tool to represent my project. And to create a unique record. You start by loading the files, confirming yes, the newest module, you are in the project folder where you believe you are, and you open your file. I use the GUI. I filter the data. I select my file. I filter the data. I go into the job correction mode. Do an initial job correction. Just decent enough. There's a bit of wave, so we might want to redo this at a later stage, but that's okay for now. Now I start by plotting. I could use an advanced or setting wavelengths, but classically just using the built-in versions is good enough for a first look. Plotting raw, as before, generates my wavelengths where I have cut out my scatter cut. It generates my kinetics, which we want to use for looking a little bit more into. It generates my measurement matrix, and it generates my SVD, which we're also keeping. So for the first fit, I would look on my data and see where is actually regions where things are happening. First, there is something happening in the very fast region, so we should have something in the 100 femtoseconds. Second, I see one decay here, which is also present here. So this is somewhere, I'm reading up here the numbers. This is somewhere in the, let's say, 4 picosecond range. So I set an initial region of 4 picosecond. Second one is I have this decay, which is somewhere in the 70 picosecond range. And now I could perform my first fit. Here I add my parameters. I set my time 0. I do not have to, but I always have it written in here. And I set my resolution, which is my spectral response function, or my temporal response function. In here I can set, I have an infinite component, which I actually do have. It's not decaying to 0. Time 0 is there. So I need to have an infinite component, which I activate. And I choose to ignore the time region for now. I'm going to work on that later. Before I do a global fit to analyze the data and plot my results, I usually perform an inspection, a visual inspection, and I turn all of the parameters vary equals false. Means I do not allow them to change. A trick which I usually use is I loop through the parameters and set them all false. Like that, my code warns, well, I have not optimized anything. My value and my initial values are the same. But what I do is I calculate the spectra. So in my matrix, I have my measured, I have my calculated matrix, and in here you see that 10 times the difference is actually not too bad. I also recognize, okay, this plot is not very good. I don't see enough contrast. So I would usually change my color scheme. And there's a number of color schemes one can use for that, depending on what you want to achieve. But for example, I usually use a lot of jet. Redoing it and the plots. become a bit more informative. So now in this plot, I see that despite using 10 times the difference, I don't see any major features, maybe a little bit here, but nothing else visible. So that is okay. This is my times. I haven't optimized anything, but also looking at my kinetics for the selected wavelengths. That's not too bad a starting point, as is my summed kinetics. Meaning that I make a reasonable start. After we have verified that the initial parameters were very close, we can now perform a fit in this range, and since we exclude this region, I will lock the first parameter to not optimize it, but to have a component which is this fast. And you can see that this is a very fast fit. You can see that the values are changed from the initial values, so there has been some optimization, and I can now visually inspect the spectra and the times. Typically, when I start by looking at the decay associated spectrum, there is no mirroring, there is no compensation. The times are in the reasonable range. They're only slightly changed from where I started. The kinetics are of course perfect, or closer to it. I don't see really any strong differences in itself. There is no features in the 2D matrix. These times are more informative. And our summed kinetics, which is very sensitive, very useful tool, also shows that this is a very good fit with no major features inside the residuals. A good estimate and the spectra of course fit very well too. Now a very good next step is to investigate how well are those parameters confined. So this is a good time for could for example run a confidence level investigation by choosing the keyword confidence level in the same global fit parameters, fit chirp stays false. One could optimize the arrival time correction. That would be by setting this to true, but setting those keywords changes the behavior of the fit global. The input in the fit global was set in the beginning as part of the parameter object. So what you do in here is you perform exactly the same analysis again of what you have just done, but now you also would like to estimate what is your confidence limit of your parameters. This optimization goes relatively fast, and we see that, for example, for each of the two parameters we have calculated what is the limits in which the statistics tells us where it can go. I didn't set any limits before, so this could go really freely everywhere, and you can see that some of those values are relatively well confined, but it is still a relatively large range. So the model we're having is okay, but maybe not good and could be worked on more. Last, before I move on and before I finish, I typically save and report. And a very nice report to save is using the function save PowerPoint, because this generates me a report file. Any of those report functions will create in the folder where your data is a subfolder called result figures, in which each of the separate plots are stored with the same name as the file, plus one output file is generated. One can of course change the file names in similar parts if one wishes. In here, in the output file, you have the raw data, which we have shown before, but now you also have a report file for your fit, which shows your difference matrices, your fit plots, and your fit parameters, always with your value, upper, lower limit, init value, and how you set it. The alignment is a bit challenging because the numbers of digits is changing strongly, but one can definitely read out the numbers. It also shows what was used for calculating the confidence level. and what is the R2 value generated. Those type of reports I typically store for each analysis together with the plot files, together with the report with the Jupyter notebook, and I can always regenerate the files. If one wishes, one can finish the analysis by saving the whole project. And then one can open up and restart the project at the same point, starting again, typing the function big S, save data, save plots, save PowerPoints, save project, and saved as it's an HDF5 file which contains everything. And saving of confidence just means that there is an object which was not saved, which we don't need for actually reporting.